One of the factors that affects the rates of reaction is what is called the energy of activation. Recall that for a chemical reaction to happen, the reactants must have a minimum amount of energy called energy of activation. This is the amount of energy that is required to overcome the mutual forces of repulsion between the reactant molecules with eventual breaking of their bonds. This energy is provided by the kinetic energy of the reactant molecules. Different reactions have their own energies of activation. We shall return to this energy profile diagram for the reaction between hydrogen and chlorine to form hydrogen chloride to review this concept. This segment from A to B represents the molecules approaching each other with their own kinetic energies. However, as the molecules get closer together, they experience mutual forces of repulsion from their negative electron clouds. If the molecules have sufficient energy and they eventually overcome these repulsions, an activated complex is formed that has the highest potential energy. Like we said before in one of the previous videos, the activated complex can do one of two things. It can reform the reactants, and in that case, all the potential energy gained will change back to the original kinetic energy of the molecules, or it can proceed to form the products. This amount of energy that is required for the products to form this activated complex is called the energy of activation for this forward reaction, and is represented by this line here. And of course, different reactions will have different energies of activation. Some will have very high energy of activation, some will have very low energy of activation. We will use the ball and stick models of two different types of molecules to see if they will react or not, depending on the amount of kinetic energy they possess and their orientations on impact. So here you have in two different sets of molecules, and these molecules are approaching each other with their own kinetic energy. Here we are seeing how the molecules are colliding, and apparently they have enough energy to break the old bonds, and new bonds are created that result in the formation of these products here. There is what is called a collision theory, and a number of concepts are involved in this theory. As illustrated and explained above, for a chemical change to happen, the particles of a chemical system, particles could be in the form of atoms, ions, or molecules, must collide with each other. The second point speaks about what an effective collision is. An effective collision happens when the reactant particles have adequate amount of energy and correct orientation to facilitate bond breaking. The following figures illustrate how a successful collision happens. The particles are having sufficient amount of energy and correct orientation. And this scenario is analogous to hydrogen and chlorine reacting as shown in the energy profile diagram above to form the activated complex and then proceeding to form hydrogen chloride molecules. The hydrogen and chlorine molecules are having enough kinetic energy and correct orientation to form the activated complex here, and then finally the products are formed. These ball and stick models here depict how a successful collision happens. They have enough energy, there's correct orientation of the molecules, and that results in product being formed. When the molecules are colliding in this way, they are said to have a greater leverage for bond breaking to happen. So these scenarios here show how unsuccessful collisions happen. Particles are having sufficient amount of energy but incorrect orientations. In such cases like these, the particles will rebound after collision and regain their initial kinetic energy without being changed. You're having a different type of collisions here. that are different from the one that we shown before that allows for bond breaking to happen easily. These types of collisions are not conducive to bond breaking, even though the molecules are having sufficient kinetic energy. Another type of unsuccessful collision happens when the molecules have correct orientations of impact, but they do not have enough energy. They have insufficient amount of energy. So again, no reaction is going to happen. Recall that as molecules approach each other with some amount of kinetic energy, it is changed into potential energy. So if a reaction is unsuccessful, the molecules will use the potential energy that they gain to push each other away. This is analogous to bringing two bar magnets with their like poles close to each other and then releasing them. This curve here shows the distribution of energy that a certain number of gas particles will have at a certain temperature, and it is called the Maxwell-Boltzman distribution curve. This axis here represents the number of molecules in any reactant system, and this axis here represents the kinetic energy that is possessed by the molecules. Analysis of this curve shows that very few number of molecules will have small amount of kinetic energy, and very few of them will have large amount of kinetic energy. The bulk of the molecules will have average amount of kinetic energy. What it is also saying is that there is a few number of molecules that will have enough kinetic energy in any reactant system to react successfully. And of course, the ability of molecules in a system to react will depend on the particular reaction, since each reaction will have its own energy of activation. Molecules that have relatively weak bonds need less energy to break their bonds and would thus react faster than those with stronger bonds to break and react. Hydrogen, for example, needs just a spark to react with oxygen, while nitrogen needs a very high temperature to do the same. Potassium reacts explosively with water, while magnesium will react only when it is very hot and with steam. So, for those molecules that have relatively weak bonds to break, they will have low energy of activation. So only that amount of kinetic energy, for example, is needed to break their bonds. So if you look at this point here, all those molecules that are shaded in this area here under the curve will react. On the other hand, molecules with strong bonds will need a higher energy of activation, and as such they will need higher kinetic energy to react. So if this is the energy of activation for one set of molecules, then only these molecules shaded in this area here would be capable of reacting. Consider the following two scenarios. Here are two beakers with equal masses of water. One is maintained at 20 degrees Celsius and the other one is maintained at 40 degrees Celsius. The levels of the water are marked by these red lines here on these beakers. The question is, what would happen to both of these beakers here if they're maintained at these temperatures and they're left open for about a week afterwards? What would you notice with the levels of the water starting with this beaker here? The answer to this will be that the levels of the water in each beaker will drop. We can see here that that was the original level of the water. Now it has dropped to that level. So why would that happen? The answer to that will be that some of the water molecules had enough energy to break their hydrogen bonds and evaporate out of solution. So the next question is, why didn't all of the water molecules evaporate at the same time? The answer to that has to do with the fact that not all the water molecules have the same kinetic energy. So we can go back to the Boltzmann distribution curve. We can say that the area under this curve represents all the molecules in the beaker of water, and only those that had enough kinetic energy, probably represented by those in the shaded area here, evaporated. And that's analogous to a chemical reaction happening. Only a few molecules with that amount of energy there will react. Next question is, how would the level of this beaker of water here compare with that one? If you say that it will depress more, then you're right. Here you can see that the level of the water is lower than in that case there. Why did that happen? And this brings us to the shape of the Maxwell-Boltzman distribution curve when the temperature of a reactant system changes. At a relatively lower temperature, only the molecules in this area here, shaded by these blue lines here, would be capable of reacting. However, at a higher temperature, we can see that there is a shift in the curve. But the area under both curves is the same. Only that in this case, there's a shift in the average kinetic energy of the molecules of the system. Because of that shift, look what happens. All these molecules that are shaded by these red dots here, including this area here, will be capable of reacting. So at a higher temperature, the average kinetic energy of the molecules gets higher. As a result of this, a greater fraction of the molecules attain their energy of activation, more frequent collision happens, and the reaction takes place at a faster rate. And that is why, at a higher temperature, the rate of the reaction will increase. It is said that for any reaction, the rate doubles for every 10-degree rise in temperature. And we can now associate this curve here with what happened with the water in the beaker being maintained at 40 degrees Celsius. At 40 degrees Celsius, the average kinetic energy of the water molecules was higher than those at 20 degrees Celsius. As a result of that, a greater fraction of the molecules was able to gain their energy of activation and cause them to evaporate out of solution. The same thing is going to happen in chemical reactions. As the temperature increases, the average kinetic energy of the molecules will increase, and a greater fraction of them will gain their energy of activation to make them react at a faster rate. The other factor that affects the rate at which reactions take place is that of the concentration of the reactants. An increase in concentration of reactants allows for more frequent collision of the particles that result in higher rates of reaction. Changes in concentration do not affect the energy of activation nor increase the average kinetic energy of the particles of the system. All it does is to bring about more frequent collision with particles. And of course, the greater the frequency of collision, the greater chance is it for a reaction to take place. Another factor that affects the rate of a chemical reaction is the presence of catalysts. A catalyst works by lowering the energy of activation for the reaction by allowing the reactions to pursue alternative pathways, thus requiring less energy for the reaction to take place. And this is illustrated by the following energy profile diagram. We have already done the energy profile diagram. So here are the reactant molecules. For them to attain this activated state here, they must be provided with that amount of energy that we call the energy of activation for the forward reaction. And that is for an uncatalyzed reaction. And you can see the relative amount of energy here. In the presence of a catalyst, the same reaction now goes through an alternative pathway involving a different reaction mechanism to form the products. But it necessitates a smaller amount of energy for that to happen. So this is how catalysts work. They increase the rate of reactions by lowering the energy of activation. Instead of all of that energy being needed, you only need that amount of energy. all because it allows the reaction to go through a different pathway that requires less energy. Hundreds of catalysts are found in living organisms, and these are called enzymes. Without enzymes, life will cease to exist. Enzymes are protein in nature and are specific in their actions. The presence of enzymes make the reactions taking place within the bodies of living organisms happen at low temperatures that are conducive to their survival. Without enzymes, therefore, all the reactions that they normally catalyze will need very high temperatures to proceed. In industries, an immense array of catalysts are used to speed up the rate at which products are formed. Most of these have been discovered by accidents or by trials. Without these catalysts, these compounds would probably be too costly to produce, as it would entail the use of lots of energy to create higher temperatures for the reactions to happen. The following are a few industrial products and the catalysts that are used in the production. The production of ammonia uses finely divided iron oxides of potassium and aluminum as catalyst. Production of sulfuric acid uses vanadium pentoxide in the contact process, and catalytic converters of automobiles use platinum and palladium to convert those toxic gases as oxides of nitrogen and carbon monoxide into safe carbon dioxide and nitrogen. Catalyst works in mysterious ways. One of the theories is that as the reactants adhere to catalysts, they become activated by having their bonds weakened. So as they exit the catalyst, it is easier for them to react. And this is illustrated below between the reaction of hydrogen and nitrogen to form ammonia. So let us say in the Haber-Bosch process that creates ammonia, this is a catalyst of finely divided iron, and those are the oxides there. These are the molecules of hydrogen and nitrogen approaching the catalyst. Of course, the catalysts are finely divided so as to create large surface areas upon which these molecules can adhere. So here we are seeing the molecules are adhering to the catalyst and they become activated. Notice the bonds here and notice the bonds here. Okay, you can see that the bonds are weakened, and because of that they are said to be activated, so they can easily be broken to form the products. And here it is illustrated how the hydrogen molecules with their weakened bonds as well as that of the nitrogen molecules are reacting to form ammonia molecules. Another factor is that of surface area. Of course, the greater the surface area between reactant particles, the greater is the chance for more frequent collisions to happen and thus faster reaction rates. So here you have a summary of the factors that affect the rates of reaction, nature of the reactants. In this case, only activation energies are different. The nature of reactant does not affect the concentration, does not affect the frequency with which they collide. Only they have different energies of activation. Go back to this Boltzmann distribution curve here. A reaction that has high energy of activation, only a few molecules will react. And one that has low energy of activation, as in this case, all of these molecules here will react. The other factor is that of temperature. Raising the temperature does not change the energy of activation, but the number of particles with higher average kinetic energy increases. Because of that, the frequency and the number of effective collisions also increases. Change in concentration of reactants does not affect the energy of activation for the reaction. The kinetic energy remains the same, only the frequency of collisions increases. Surface area, everything stays the same, but because you're increasing the surface area of the reactants, there's greater frequency of collision between them. And of course that will increase the rate of the reaction. And then we have catalysts. The kinetic energy and the frequency of collision stays the same, but the energy of activation is lowered. Only the energy of activation is lowered, everything else remains the same. Bringing all of these together, we can say that the rate of reaction is equal to frequency times fraction of effective collision. The frequency is affected by concentration, surface area, and temperature. Fraction of effective collision is related to the temperature, and it's also catalyst. So thank you for listening. I hope that was useful.